Dear students, today we continue infinite series. In this lecture, we discuss some comparison tests which are used in infinite series to check the convergence and divergence of positive term series. The first theorem, say first form of comparison test, if summation n is equal to 1 to infinity an and summation n is equal to 1 to infinity bn are two positive terms series and k is any fixed positive constant such that an less than equal to k times of bn for all n, then show that if summation n is equal to 1 to infinity bn is a convergent series, then summation n is equal to 1 to infinity an is also convergent series. Also show that if summation n is equal to 1 to infinity an divergent series, then show that summation n is equal to 1 to infinity bn is also a divergent series. In that comparison test, there are two infinite series, two infinite positive term series whose nth term satisfying the following inequality: an is less than equal to k times of bn for all n, then show that if bn is convergent, then an is also convergent. If an is divergent, then bn is also divergent. To prove this, here it is given that an is less than equal to k times of bn for all n. Putting n is equal to 1, 2, 3 and so on, we have a1 less than equal to k times of b1, a2 less than equal to k times of b2, continue like this, an less than equal to k times of bn. Adding these vertically, we have a1 plus a2 plus a3 plus an less than equal to, from that term taking common k, b1 plus b2 up to bn. Let Sn and Sn dash. Sn and Sn dash denote the Sn and Sn dash denote the first sum of first n term of the series an and bn respectively. So therefore Sn is the sum of first n term of the series an, so that can be written as a1 plus a2 up to an. Similarly Sn dash denote the sum of first n term of the series bn. So therefore Sn dash can be written as b1 plus b2 up to bn. So therefore from 1 that term is equal to Sn and that term is equal to Sn dash. We have Sn less than equal to k times of Sn dash for all n. Now take the first part. In the first part, it is given that series bn is convergent. We have to show that series an is also convergent. So for part first, if the series bn is convergent, we know that if a series is convergent, then sequence of nth partial sum of that series is also convergent. So the sequence Sn dash is also convergent, and we know that every convergent sequence is bounded. Every convergent sequence is bounded, so it is bounded above. So therefore sequence Sn dash bounded sequence is bounded below as well as bounded above. So therefore sequence Sn dash is bounded above. So it is a positive term series whose nth partial sum is bounded above. So therefore by the definition of bounded above, there exists a positive real number k dash such that Sn dash is less than k dash for all, and by the definition of bounded above, here sequence Sn dash is bounded above, then by the definition of bounded above, there exists a positive real number k dash such that Sn dash is less than equal to k dash for all, and उस सीक्वेंस की हर एक टर्म किसी न किसी एक रियल नंबर से क्या मिलेंगी, छोटी मिलेंगी. तो from equation number 2 and 3, here is equation number 2, Sn is less than equal to k times of Sn dash for all n, and here is equation number third, Sn dash is less than k dash. Combining these two equation, we have Sn less than equal to k, or replacing Sn dash by k dash, we have Sn dash is less than equal to k into k dash. So this implies sequence Sn is bounded above. The sequence Sn is bounded above. So therefore, by general test for convergence of positive term series, series An is also convergent series. Now we prove the second part. In the second part, if series An is divergent, we have to show that series Bn is also divergent. To prove this, here it is given that if series summation n is equal to 1 to infinity an is divergent series, अगर ये divergent series है तो इसकी जो nth पार्शियल सम की सीक्वेंस होगी वो हमारे पास क्या होगी, अनबाउंडेड अबोव होगी. तो दिस इंप्लाइज सीक्वेंस Sn is unbounded above. By the definition of unbounded above, for each positive real number k dash, however large it may be, there exists a positive integer m such that Sn that is unbounded above, so Sn is greater than k dash into k for all n is greater than equal to m. So therefore from equation number 2, here Sn is less than equal to k times of Sn dash. In reverse order, we read k Sn dash greater than equal to Sn, and Sn is greater than k dash into k. Combining these, we have k Sn dash greater than equal to Sn is greater than k dash into k. So from this we have Sn dash, from this k से k cancel हो जाएगा और Sn dash is greater than k dash for all n is greater than equal to m. This implies sequence Sn dash is unbounded above, therefore by the definition series Bn is also divergent. Okay, clear students? Now we discuss second comparison test. In second comparison test, if summation n is equal to 1 to infinity an and summation n is equal to 1 to infinity bn are two positive term series, and small k and capital K are two positive numbers such that k times of bn less than equal to an is less than equal to capital K times of bn for all n, then the series an and bn converges or diverges together. Here in the second comparison test, it is given that there are two positive term series an and bn which satisfying the following inequality: k times of bn less than equal to an less than equal to k times of bn for all n. In that situation, both the series an and bn converges or diverges together. Now we prove this comparison test. Here it is given that k times of bn less than equal to an less than equal to capital K times of bn for all n. From say equation number 1, taking from equation 1 that part an is less than equal to k times of bn for all n. Therefore by first form of the comparison test, if series bn is convergent, then series an is also convergent, and series an is divergent. If series an is divergent, then series bn is also divergent by the first form of the comparison test. Also from equation number 1, taking that part k times of bn less than equal to an, which can be written as bn is less than equal to 1 by k times of an. Therefore again by first form of the comparison test, an series is convergent. If series an is convergent, then series bn is also convergent. Also by first comparison test, if series bn is divergent, then series an is also divergent. So now combining part say 1, part 2, part 3 and part 4 means, if we take part 1 and part 4, here part 1, if series bn is convergent, an is convergent, bn is divergent, an is divergent. Similarly, in part 2 and 3 we see that if series an is divergent, bn is divergent, an is convergent, bn is convergent, therefore the series an and bn converges and diverges together. Clear? Now we discuss next comparison test, say third comparison test. In third comparison test, yeah, third form of comparison test, here it is given that if summation n is equal to 1 to infinity an and summation n is equal to 1 to infinity bn be two series of positive terms such that an is less than equal to k times of bn for all n greater than equal to m. Here is the difference between first form and second form. In the first form, here is for all n, and in the third form, here is for all n greater than equal to m. Here m being a fixed positive integer and k is any positive number. So show that if bn is convergent, then an is also convergent. If an is divergent series, then bn is also a divergent series. So part first form and second form, first form and third form are almost similar. First form is true for all n, and third form is true for all n is greater than equal to m. So their proof are similar. To prove this, let us consider Sn and Sn dash denote sum of first n term of the series an and bn respectively. So therefore Sn can be written as a1 plus a2 up to an. Similarly, Sn dash can be written as b1 plus b2 up to bn. Since here it is given that an is less than equal to k times of bn for all n greater than equal to m. It is given, or that inequality is true for all n is greater than equal to m. So therefore we can be written as am plus 1 plus am plus 2 up to an less than equal to k times of bm plus 1 plus bm plus 2 up to bn, because this inequality is true for all n which are greater than equal to m. So that term can be written as Sn minus में Sn, sum of n terms minus sum of first m terms, which is less than equal to k times of that term can be written as Sn dash minus में Sm dash for all n is greater than equal to m. So from this Sn, taking Sm in the right hand side, we have k times of Sn dash plus Sm minus k times of Sm dash. Here Sm represent the sum of first m term of the series an. Sm dash represent the sum of first m terms of the series bn multiplying by a number k. Then we get that is a finite quantity, a fixed finite quantity, and let that term is equal to any real number, say k dash. So therefore we have Sn is less than equal to k times of Sn dash plus में k dash, where k dash is equal to Sm minus k times of Sm dash for all n is greater than equal to m. Here Sn dash is equal to k Sn dash plus में k dash, where k dash is equal to Sm minus k times of Sm dash, where k dash is a fixed finite quantity. Now part first, if summation n is equal to 1 to infinity an bn is convergent. For part first, if summation n is equal to 1 to infinity bn is convergent, तो कन्वर्जेंट अगर कोई भी सीरीज कन्वर्जेंट होगी तो उसके जो nth पार्शियल सम की सीक्वेंस होगी वो भी हमारे पास क्या होगी, कन्वर्जेंट होगी. और कोई भी सीक्वेंस अगर कन्वर्जेंट है तो वो बाउंडेड होती है, अगर वो बाउंडेड है तो वो बाउंडेड बिलो भी है, तो बाउंडेड अबोव भी है. तो सीरीज इज कन्वर्जेंट, तो Sn dash is bounded above. तो from this if Sn dash is bounded above, then k times of Sn dash, if k is any positive real number, then that is also bounded above, and plus k dash, that is also bounded above. So from this we conclude that sequence Sn is also bounded above, and then by the general test of convergence, general test of convergence for series, we have summation n is equal to 1 to infinity an is also convergent. Second part, in the second part, if summation n is equal to 1 to infinity an is divergent, then bn is also divergent. Here summation n is equal to 1 to infinity an is divergent. We know that if a series is divergent, then the sequence of nth partial sum of that series is not convergent, means it is not convergent, means it is not bounded above, so it is unbounded above. So sequence Sn is unbounded above. So therefore from equation 2, if Sn is unbounded above, then Sn dash is also unbounded above. So therefore from 2, sequence Sn dash is also unbounded above. So therefore series summation n is equal to 1 to infinity bn is divergent. Clear students? In the third form of comparison test, here हमारे पास दो सीरीज दे रखी हैं, एक समेशन n इज इक्वल टू 1 टू इन्फिनिटी an है एंड एक समेशन n इज इक्वल टू 1 टू इन्फिनिटी bn है, विच सेटिस्फाइंग द फ्लोइंग कंडीशन an is less than equal to k times of bn for all n is greater than equal to m, where m is any fixed positive integer. We have to show that bn convergent then an convergent, an divergent then bn divergent. To prove this, we follow the following rules, and I think all the students understand that. Okay. Now we discuss next comparison test, say fourth form. In the fourth form, if an and bn are two positive term series and small k and capital K are two positive number such that k times of bn less than equal to an less than equal to k times of bn for all n greater than equal to m, that inequality is same as second form. In second form, that is true for all n, and that is true for n is greater than equal to m for some fixed positive integer m. Then show that series an and bn converges or diverges together. Do yourself same according to second form. Next result is important result. And fifth form, if an and bn are two series of positive term such that limit n goes to infinity an by bn is equal to l, where l पर कंडीशन है कि l हमारे पास क्या हो, या तो फाइनाइट नंबर हो या वो फिर एक नॉन जीरो हो. मीन्स l हमारे पास कोई भी एक फाइनाइट नंबर हो या फिर वो नॉन जीरो है. इसका मीनिंग यह हुआ कि l ना तो जीरो हो, l की वैल्यू जीरो नहीं हो सकती, और ना ही l इनफाइनाइट हो सकता. तो then both the series an and bn converges or diverges together. That comparison test is important for numerical problem also. For numerical problem, take the nth term of the series first, take the bn nth term of the series second, and divide these, and taking limit n goes to applying limit n goes to infinity, and we get what value. After that, if value is finite and non-zero, then we say that series an and bn converges or diverges together. To prove this, here the series an and bn both are positive term series, so therefore nth term of first series and bnth term of the second series both are positive, because the series are positive term series for all n greater than for all n. So therefore an by bn, that is greater than 0, so therefore an by bn is also greater than 0 for all n. Taking limit n goes to infinity an by bn, लिमिट लगाएंगे nth term by bn an by bn पे, that also goes to 0, otherwise that is greater than equal to 0. तो limit n goes to infinity an by bn is also greater than equal to 0. और let limit n goes to infinity an by bn is equal to l, so therefore l is also greater than equal to 0. But l is not equal to 0, L is not equal to 0. Here given that L is finite and non-zero, so this therefore L is greater than 0. So here we conclude that sequence a and bn sequence here from that limit n goes to infinity a n by bn is equal to L, or where L is greater than 0 means sequence a and bn converges to L. So then by the definition of the convergence of a sequence for given epsilon is greater than 0, uh, we choose epsilon is greater than 0 such that L minus epsilon is also greater than 0. Since limit n goes to infinity, a n by bn is equal to L, therefore by the definition of the convergence of a sequence, there exists a positive integer m such that mod of a n minus bn minus L is less than epsilon for all n is greater than equal to m. From this a n by bn less than L plus epsilon greater than L minus epsilon, multiplying by bn on both sides, bn through the inequality, L minus epsilon bn less than an L plus epsilon bn, take L minus epsilon by small k and L plus epsilon by capital K. We have k times of bn less than an less than k times of bn for all n is greater than equal to m. So therefore by the comparison test for in comparison test for if k times of bn less than equal to an less than equal to k times of bn for all n is greater than equal to bn, then the series an and bn converges or diverges together. Here is also the same situation, k times of bn less than an less than k times of bn for all n is greater than equal to m. Therefore by the comparison test fourth form, the series an and bn converges or diverges together. Now we discuss some remark on that comparison test number 5. In the above theorem and in comparison test 5, the condition limit n goes to infinity a n by bn is finite and non-zero cannot be dropped. इसको छोड़ा नहीं जा सकता कि जो कंडीशन है कि लिमिट n goes to infinity ए एन बाई बी एन एन गोस टू इन्फिनिटी लगाने पर जो एल आएगा वो हमेशा क्या होना चाहिए, फाइनाइट एंड नॉन जीरो. अगर वो जीरो और या इनफाइनाइट हो जाता है तो ये रिजल्ट, ये थ्योरम कैन नॉट बी अप्लीकेबल. दैट कंपैरिजन टेस्ट कैन नॉट बी अप्लीकेबल. फॉर एग्जांपल कंसीडर ए एन 1 बाई एन, बी एन 1 बाई एन स्क्वेयर, ए एन बाई बी एन लिमिट एन गोस टू इन्फिनिटी अप्लाई करके हमने देखा ये हमारे पास क्या जाता है, इनफाइनाइट आता है. इनफाइनाइट मीन्स एल इज इक्वल टू क्या जाता है, इनफाइनाइट. तो इसका मीन्स द कंपैरिजन टेस्ट 5 कैन नॉट बी अप्लीकेबल फॉर दैट सीरीज. तो मीन्स सीरीज ए एन एंड बी एन डू नॉट कन्वर्जिज और डाइवर्जिज टुगेदर, बिकॉज जो सीरीज हमारे पास समेसन ए एन 1 बाई एन समेसन एन इज इक्वल टू 1 टू इन्फिनिटी 1 बाई एन जो है वो हमारे पास एक डाइवर्जेंट सीरीज है, और जो बी एन 1 बाई एन स्क्वेयर है वो सीरीज हमारे पास क्या है, एक कन्वर्जेंट सीरीज है. तो बोथ आर नॉट कन्वर्जेस और डाइवर्जेस टुगेदर बिकॉज हेयर एल इज इक्वल टू इनफाइनाइट. सिमिलरली वी कंसीडर एन एग्जांपल second, an is equal to 1 by n square which is a convergent series, bn is equal to 1 by n which is a divergent series. लिमिट n गोज टू इन्फिनिटी an बाई bn किया, लिमिट n गोज टू इन्फिनिटी an की वैल्यू पुट की, bn की वैल्यू पुट की और सोल्व किया हमने, वो जीरो आ जाता है which is equal to L. तो here L is equal to 0 which is non-zero, L is equal to 0 which is not non-zero. So comparison test 5 cannot be applicable here. So therefore A and Bn do not converges or diverges together because here that An जो given है वो हमारे पास एक convergent series है और Bn जो हमारे पास है वो एक divergent series है. तो इसका मीनिंग ये हुआ कि फिफ्थ जो कंपैरिजन टेस्ट है उसमें जो एल पर कंडीशन है वो हमेशा क्या मिलनी चाहिए, फाइनाइट और नॉन जीरो होगी, तभी वो फिफ्थ कंपैरिजन टेस्ट एप्लीकेबल है. अगर एल की वैल्यू जीरो या इनफाइनाइट आ जाती है तो फिफ्थ कंपैरिजन टेस्ट इज नॉट एप्लीकेबल. नाउ वी डिस्कस नेक्स्ट थ्योरम. If summation n is equal to 1 to infinity an and summation n is equal to 1 to infinity bn, b are two positive term series such that limit n goes to infinity an by bn as a l, means in that case when l is equal to 0 here, in that case it's depend on the नेचर ऑफ द सीरीज बी एन. इफ सीरीज बी एन हमारे पास कन्वर्जेंट हो जाएगी, नीचे वाली जो सीरीज है बी एन अगर वो कन्वर्जेंट होगी तो हम ऊपर वाली के बारे में कह सकते हैं कि सीरीज ए हमारे पास क्या होगी, कन्वर्जेंट होगी. सिमिलरली लिमिट एन गोज टू इन्फिनिटी एन बाई बी एन अगर इनफाइनाइट आ जाता है, मीन्स एल की वैल्यू इनफाइनाइट आ जाती है, वो हमारे बी एन की नेचर पे डिपेंड करेगी. अगर सीरीज बी एन हमारे पास डाइवर्जेंट है तो हम ए एन के बारे में बता सकते हैं कि वो ए एन भी हमारे पास डाइवर्जेंट होगी. मीन्स इन केस इफ लिमिट एन गोज टू इन्फिनिटी एन बाई बी एन इज इक्वल टू 0 है, तो जो सीरीज अगर बी एन कन्वर्जेंट है तो ए एन हमारे पास कन्वर्जेंट होगी. अगर ए एन कन्वर्जेंट हो तो बी एन के बारे में हम कुछ नहीं कह सकते. इसी टाइप से ए एन बाई बी एन हमारे पास इनफाइनाइट है, तो बी एन अगर डाइवर्जेंट है तो ए एन डाइवर्जेंट होगी. अगर बी एन कन्वर्जेंट है तो हम ए एन के बारे में कुछ नहीं कह सकते. ओके, क्लियर स्टूडेंट्स? तो दैट रिजल्ट शोज दैट we limit n goes to infinity an by bn is equal to 0 हमें given है, means sequence an bn converges to 0. तो therefore by the definition of the convergence of a sequence for given epsilon is greater than 0, there exists a positive integer m such that mod of an minus bn minus 0 less than epsilon for all n greater than equal to m. So therefore an by bn less than epsilon greater than minus epsilon for all n greater than equal to m. Multiplying by bn we have minus bn dot epsilon less than an less than bn dot epsilon for all n is greater than equal to m. From 1 we have an is less than equal to epsilon times of less. From 1 we have an is less than epsilon times of bn for all n greater than equal to 1. Therefore summation n is equal to 1 to infinity bn is convergent. Therefore for part first, if an by bn is equal to 0, अगर bn कन्वर्जेंट है तो हमें बताना है कि an भी कन्वर्जेंट होगा. तो for part first bn is convergent, तो an is also convergent by the comparison test third. By the comparison test third, that case for comparison test third, in the comparison test third. Similarly when n limit n goes to infinity an by bn is equal to infinite, means sequence a and bn is a divergent sequence, so it is a divergent sequence, so it is a unbounded sequence. Unbounded sequence, therefore by the definition of unbounded sequence, for any positive real number k, for any positive real number k however large it may be, there exists a positive integer m such that an by bn is greater than k by the definition of unbounded sequence for all n is greater than equal to m. So this implies an is greater than k times of bn for all n is greater than equal to m. So for second part, if bn is divergent, we have to show that an is also divergent. Let summation n is equal to 1 to infinity bn is a divergent, or therefore by the comparison test third, again we have summation n is equal to 1 to infinity n is also divergent. Clear? Okay students, thanks.